Hello, everyone. Uh, I really was hoping not to do this semester, but for the first time in a while, I am actually sick, which you can probably hear in my voice. So we're going to do this way so that hopefully none of you become sick. I hope you'll do the same if you are sick. But today, we're going to talk about section 1.3. The due dates for the homework are the same. They're listed on Katie. So tonight at midnight, the homework for 1.2 is due. On Wednesday at midnight, the homework for 1.3 is due, which we're going to talk about now. If you do have any questions about the 1.2 homework in advance of turning it in, feel free to email me because I know I'm not there to sort of answer it in person as one would hope, but these things happen. So our topic today is going to be linear models. And so basically our goal when we talk about linear models is going to be to connect something that looks like a bunch of dots, as you've seen most of our data sets do, with something that looks more like the things that you would graph in, say, Math 140 or some other pre-calculus calculus course that you've had, some nice little curves. So the things that you're used to thinking about, like f of x equals x squared. In fact, actually, since today we're talking about linear models, we're really only going to be talking about things that look like y equals mx plus b. But the first thing that I want to do is I want to encourage you, for purposes of this course, not to think of the equation for lines in that way, and instead to think about the equation of lines as being the point-slope formula. And what the point-slope formula gives you is it gives you that y is equal to m times x minus x naught plus y naught. This is the line of slope m that passes through x naught, y naught. Now, in many classes that you've had before, likely you were always told, convert everything back to mx plus b form. Here, we're very specifically not going to want to do that. And you'll see why as soon as we do an example as to why that would probably not work out actually super well at all. So what are our questions in this section going to look like? We're going to be asked to do something like make a linear model for the college tuition data. Okay, so to do that, we're going to have to, of course, dig up the college tuition data, which happens to be here. Dump it into Desmos. And now I want to point out, I specifically told you to make a linear model for this. That is to make a line that looks like these dots. But I want to point out, even if I hadn't told you that, actually these dots look quite a bit like they're going to be a line anyway. There's only this small little wiggle that doesn't look almost exactly like a line as it is. And so what is it we're going to do? Well, we're going to try and sort of find a line that looks as much like this as possible. Okay. And we're going to do this effectively by smart trial and error. Because remember, I know that the form of the line is going to look like y equals m times x minus. And so what I'm going to recommend you do when you're trying to fit a linear model to an equation is sort of pick the center of the data. So in this case, that's 2010 plus, and then the value at 2010 is, just by looking up there, it is 22,677. Okay. So what I've done there in Desmos by typing this and clicking the add slider button is I've given myself a line, in this case of slope 1, that passes through the center point. Now, I don't have to keep that it passes through that center point. I can change that if I want. But what I can do now is I can wiggle around this m and it will adjust the equation for me. Now, you'd have to have a really fancy monitor to see that it's actually wiggling at all. If you're watching this on your phone, you probably can't. And that's because the line I'm looking for has slope way more than 10. As always with Desmos, if you want to change something, you have to do something really unintuitive. So click the 10 on the end, and we'll say we want our slider to go from slope 1, and let's just have it run all the way up to 1,000. Okay. So now, instead of Desmos letting me wiggle this line through slopes between 1 and 10, it's letting me wiggle this between slopes of 1 and 1,000. And so if I do this, now you can see as I drag the line, it actually changes the slope in a perceptible way. Now, as I do sort of drag this around, I notice that something like this is pretty close, but it should be a bit higher if I want this to look as much like the data set that I'm looking at as possible. So I can just try here to make this, say, 23,000. And that's not quite high enough, so let's add another 1,000. And that's maybe a bit too high, so we go to 23,500. And that's a pretty darn good fit if you look at it. The years along the line, the data points never actually get very far at all from the line that we drew. Now, of course, we want to make sure we present our data well. So we're going to be sure we label that this year, that axis is year, this axis is tuition. And I think when you're trying to write down a model like this, I think often it helps if you have Desmos show the line as dashed. You can do it however you want, just to make it visually distinct from the underlying data that you're looking at. But this here, this is our linear model. So I'm going to copy that down on the sheet of paper. And note when I do that, I'm instead of writing Y, I'm going to write a capital T, because that's the letter we've used for tuition, is equal to, and now M is 890 times, and then lowercase t minus 2010 plus 23,500. Okay, so I'm just copying that off the screen. And you can see there, I just copied the line. Okay. So anytime you write down an equation like this, it's worth thinking about what do all of the numbers here actually mean? And in particular, what are the units of those numbers? So what is this 890? I suppose I'm really only talking about what about this? What is this 2010? And what is this 23,500? The 2010 and the 23,500 are almost but not quite an input-output pair from the original data set. Because remember, this is the line written in point-slope form. So that's the slope. We'll talk about that in a second. And then we're talking about this line is passing through x0, y0. So this line is passing through 2010, 23,500. And so the 2010 here is an input. It's the year. So these two together are saying that in the year 2010, the tuition was $23,500. Okay, and notice this is a year, this is dollars, because that is how our data works. So what if I convert this to y equals mx plus b form? Just to see it. What does this look like in y equals mx plus b form? Well, it would look like t of t equals 890t. And then let me calculate this off screen real quick. And I'll spare you watching me multiply these numbers out, but it works out to be minus 1,765,400. And so when we're talking about why it is I prefer this one to this one, the reason why I do prefer that is because I want to think about what does this number mean? Well, what is the b in y equals mx plus b? Well, the answer is it's the intercept. So it's the y-intercept specifically. Okay. But what is a y-intercept at the end of the day? At the end of the day, the y-intercept is the value of the function when you plug in 0. But what is it I'm plugging into this function at all? I'm plugging in a year to get out college tuition. So roughly speaking, if I were to translate this, what this would say was, in the year 0, the average college tuition was negative $1.7 million, which is complete nonsense, right? There's absolutely no way that this is true. This is just complete nonsense. Okay. Going back to our data set, remember that our data set actually only went back to 2001 and forward to 2019. So our data set covered 20 or so years. If we try and go back to the year zero, I mean, for all of the many, many reasons why that's absurd, not the least of which is that probably no one's going to pay you $1.7 million to go to college. Our data set does not let us say anything about this. You should, in general, always be worried about what's often called extrapolation. An extrapolation is just values outside the range of your data set. Right. So quite often it's going to be the case that the extrapolations are going to be the things you're most interested in, because they're going to say things like, what will the college tuition be in the future? But you also have to worry about maybe things won't keep going the way they are now. So it's not that you can't extrapolate, but do so with some caution. And in this case, if you try to extrapolate out to the year zero, obviously nonsense things are going to happen. But that said, let's try and do a much more reasonable extrapolation. So let's try and guess, what do we think the college tuition will be? And let's pick 2025. So 2025 is still extrapolating because it's still outside the realm of my data set, but it's not outside it by so much that it's necessarily unreasonable to believe that this is likely what the answer is going to be, or that the answer will be here. So we can certainly estimate it, and we can guess it's going to be about, and so you can see where my cursor is, 2025, 36,850. But if you want, you could just go back to our model. All we're doing here is taking our model, which was this, and we're plugging in 2025. So T of 2025 is 890 times 2025 minus 2010 plus 23,500. And so if I then pull up my Desmos scientific calculator here and type that in, we'll get 890 times 15. I'm just going to do the 2025 minus 2010 in my head, plus 23,500. And that will be where we get our estimate of 36,850. And remember, that's in dollars. Now, the thing I want to focus on here is the slope. So the slope of our model is 890. And I want to think about what are its units and what does it mean. Now remember, functions always have an input and an output. And it's easy to describe the units of slope in terms of the input and the output's units. So indeed, the units of slope will always be the units of the output divided by the units of the input. So in this case, my function's input is a year, and the output is the cost of tuition, which is in dollars. So the units here are in dollars per year. Now, remember what slope is. Slope is always change in output or change in input. As I told you, this is a calculus course, and calculus is all about change. Slope is one of the easiest ways we have to measure change. Namely, it measures how much the output changes per change in the input. So for example, if the slope is 2, it's saying the output changes twice as quickly as the input. If the slope is 200, it's saying the output changes 200 times as much as the input. In this case, our slope is $890 per year, meaning that according to our model, Tuition is in fact rising at that rate. So what this is saying is that according to our model, the tuition is rising by $890 per year. If I go back to look at this T of 2025 and look at what the math I actually ended up doing over in Desmos in a second, you'll see that what we literally did was to take 890, the number of dollars that it was changing by per year, multiply it by the number of years that the number we're interested in 2025 is after 2010, and then add the value that was already there at 2010. You can see that here. 15 years after 2010, when we pegged the value at 23,500, the value had gone up by 890 15 times, which is where we got this, and where we got this 36,850. Okay. Again, that's why I'm encouraging you to use this point slope format for a line rather than the y equals mx plus b format, because you actually can interpret all of the numbers that go into and come out of it in a meaningful way that you just can't if you try and translate everything back to y equals mx plus b. Next up, we're going to look at this cricket temperature data. So here we have some data about crickets. And in particular, what the data tells you is how many chirps this particular type of cricket makes per 15 seconds based on what the temperature outside happens to be. So this is a bunch of observed information. Now, I could just copy paste this and then just dump it into a new Desmos window, and it would be fine-ish. But this is not really the order that I want these two things in. And let me tell you why. The reason why is that usually when we want to communicate two things that are related, but the first is causing a change in the second, we usually want the thing that's causing the change to be our input. So in this instance, what I'm saying is the rise or fall in temperature is changing how the crickets chirp. It's not the case that if you make the cricket chirp more or less, it will raise or lower the temperature. And so as a result, when I go to actually display this, I really want to actually display it in the other order. So to do that, you'll have to go ahead and make up your own spreadsheet, and you'll have to drag these two columns to be in the other order. Now, once we've done that, now we can copy it and paste it into Desmos. Okay, let us make sure, again, that we are careful about labeling our axes. So we have set it up here. So specifically, the x is temperature in Fahrenheit. And the y-axis is cricket chirps per 15 seconds. This data set also looks roughly linear in shape. Again, this one's maybe a little bendier, but we can certainly draw a line that helps us get through here. So again, I'm going to do the same thing I did last time, which is to start with m times x minus, and I'm going to grab the point at 68, not for any particular reason, it's just sort of kind of in the middle, plus 32.6. I'm going to add a slider for m. And wow, actually that got pretty close, if I'm being honest. The thing that I most want to do is I most want to lower this a bit. And if you want, you can even put a b here and add a slider for b. And you can slide b around, although of course here our b before was 30 something, so we can go for say 25 to 35. Yep, there we go. So now we can slide this until it looks right. Now that doesn't look quite as sharp as it should, so maybe I can slide the slope up a little bit. And eyeballing it, I end up with something like that. Let me move it just so you can see the top points up here, because I realize you could not see them behind my camera. So let's bring that up to 120 just so that my camera's not blocking the graph. So you can see, again, I chose a line here, sort of goes through as much as possible the center of all of these pieces of data. Okay. Again, maybe you want to make the line dashed so that you can see it like that. That's our linear model. So our linear model is, so it is chirps equals 1.2 times x minus 68 plus 30.87. And the 87 is probably more decimal digits than we really need to do this. So here I've written down what our linear model is that we found. And we can comment on how good the fit is. And so a perfect fit would mean the line passed through literally every point. Ours doesn't quite do that, right? This is not quite here. But I would describe this fit as pretty good. Passes through the middles of all of these various dots. That's all good. So you'll want to think about, when you're making a model, how good your model actually is. And real data has noise in it. So sometimes it's not going to be perfect. Sometimes it's going to be weak, but you'll use it anyway. Now, if you look at the original spreadsheet, you'll see that it gives you something called Dolbear's law. And Dolbear's law says that the temperature in Fahrenheit is equal to the chirps plus 40. Now, who is this for? This is for hikers. Because if you're out hiking in the middle of nowhere and maybe you don't have a thermometer on you, you probably do have a phone that can keep track of the amount of chirps that a cricket makes in 15 seconds, and you can use that to estimate what the temperature in Fahrenheit is. So now what we can do is we can compare Dolbear's law to the fit that we actually have over here back in Desmos. Now, one thing you'll notice is that Dolbear's law is set up so that the input is the number of chirps for a cricket and the output is the temperature, because the use case of this particular law is computing the current temperature. But if we want this to show up on our graph, where what we have is actually cricket chirps in terms of temperature, we have to rewrite this rule the other way. And so what I have to do is I have to actually solve for C and get that C is equal to T minus 40. And so if I now type that in over here, y equals x minus 40, this red line now is Dolbear's law. So just to show you only one of them at a time, that's the Dolbear one. That's ours. Now, I try to be humble, but I think we did way better than Dolbear's fit here. Dolbear's fit here looks to me like we've missed very consistently low, and maybe the slope isn't quite right or something like that. So I think actually our fit is better. Why do I think that is? I think the reason why that is that the use case of Dolbear's law is to be easy to remember for a hiker and easy to compute for a hiker. And so if our rule were what you told the hikers, hey, if you want to know what temperature it is, just remember this handy dandy formula with a 1.2 in it, then well, none of them are going to remember it. And so the joy of Dolbear's law is that it's an incredibly easy formula to remember, and maybe it's not perfect, could be a little better, but in terms of something that you can do in your head, it's pretty efficient. Okay, I'm going to do a couple more questions with our linear model. So I'm going to write it out like this, and I'm going to round this number because this number has way more decimal points than we could ever possibly want. So I have this written as 1.2 times t minus 68. And yes, if you caught me before, I did write this as x before, but I should not have, because this thing stands for temperature. So it should certainly get a letter that reasonably stands for temperature. So t is a good choice. So that is what I am using here. So this is our model. What can we do with it? Well, we can answer questions like, if it was 75 degrees outside, how often would you expect the crickets to be chirping? So you could look at the data set and you can see, provided I hit the button, if you look at the data set, you can see I don't have a 75. I have a number that's at 78 and one that's at 73.5. So I can't directly estimate this answer from the graph. But what I can do is I can plug in 75 into my linear model. So the way we're going to do this is by calculating C of 75, which is 1.2 times 75 minus 68 plus 31. And no reason to try and do that in our heads or anything like that. Let's just hop straight over to the scientific calculator here and see what it says. So 1.2 times 75 minus 68 plus 31 is equal to 39.4. And again, remember, we should be paying attention to what this 39.4 actually represents. This 39.4 is chirps per 15 seconds. Now, if you go back to the original data set and look at this and see if that seems reasonable, we can look at, say, there's where it was at 78. It was at 43.6. Here's where it was at 73.5. It was at 35. So probably we should expect it'll be somewhere in between these two. This is indeed between those two, this 39.4 that we got as our answer. So that seems reasonable. It seems as good as we're going to be able to do for this question. Now, we can ask the question the other direction just as easily. So I could ask you, hey, if the crickets are chirping at a rate of 50 times per 15 seconds, what temperature do we estimate it is? And again, to do that, we just go back directly to our linear model. And what do we plug in? We plug in the 50. But the 50, remember, is not the temperature. The 50 is the chirps. And that's one of the real advantages here of using these different variable names, is that if I'm talking about chirps per 15 seconds, I better plug it in for the C variable and not for the T variable. So what I'll get is 50 equals 1.2 times T minus 68 plus 31. So I can go ahead and subtract 31 from both sides. That's going to leave me 19 on this side is equal to 1.2 T minus 1.2 times 68. And so T is going to be 19 plus 1.2 times 68 times divided by 1.2. Now, notice I could have sort of calculated that here, but when I'm going to be dealing with messy numbers anyway, which, spoiler, in this class you're usually going to be dealing with messy numbers anyway, I might as well wait to deal with the messy numbers until I'm directly entering the thing into my calculator. So let's directly enter this into the Desmos calculator. Sorry, the wrong thing. Let's directly enter this into the Desmos calculator as 19 plus 1.2 times 68 divided by 1.2. And that gives us our answer, which is that we estimate that it's 83.3 degrees Fahrenheit. Can again go back to our data set and look and see if we believe that's reasonable. And we see that lies a little bit outside of our data set because we didn't ever see 50 chirps per second. But at least it's sort of in the ballpark of where we saw some numbers. So hopefully this is accurate. Now, it's worth noting, if you zoom out here, this is just a line. So it has an x-intercept right around here. And it has a y-intercept. And it's a natural question to ask, does this x-intercept and this y-intercept mean anything? So, first of all, what's the x-intercept here purporting to tell us? The x-intercept is purporting to tell us that if the temperature is 42.275 degrees Fahrenheit, then the crickets will chirp 0 times per 15 seconds. You might, for example, believe that this means that that temperature would kill crickets, or at least make them dormant. Now, that is a ways outside of our actual data, so whether you trust that or not, that's up to you. That's at least plausible, but I would regard it with some skepticism. What about the y-intercept? The y-intercept is telling me that if the temperature outside is 0 Fahrenheit, that the crickets are chirping at a rate of negative 50.7 chirps per 15 seconds. Okay. That I just know flat out is nonsense, right? There's no way the crickets are chirping at a negative rate. So that I can just immediately disregard when I go to do this. So this one, the x-intercept, maybe you can ascribe meaning to it. You can certainly say what it would mean if it were accurate. You can be a little skeptical about whether it will actually be accurate. The y-intercept is just completely meaningless. So keep that in mind. Slope itself is always a measure of change. And it's really a way of talking about change and answering two fundamental questions about change. The first is, how fast is a thing changing? So when we talked before about the college tuition and we got that the slope was $890 per year, that was telling us how quickly the tuition was going up. But also, slope tells you which direction things are changing. So when we talk about something having positive slope, that means that the two things that we're looking at, the input and the output, they move in the same direction. So if one goes up, the other goes up. If one goes down, the other goes down. And on the other hand, if we're looking at a negative slope, then what that's saying is that they move in opposite directions. If one goes up, the other goes down. If one goes down, the other goes up. Okay. Now, this should sound familiar because this is exactly the same story that we told when we talked about correlation. Namely, positive correlation means two things move in the same direction, and negative correlation means two things move in opposite directions. So the slope and the correlation, and those words, they mean the same thing. Okay. Again, zero correlation or zero slope mean that one changing just doesn't affect the other at all. So there's no link between the two things at all. All right, I'm going to wrap up there for today. That should be plenty for you to do all of the 1.3 homework. Email me if you have questions. I hope to be back on Wednesday. No promises. You'll either see me back or you'll get another of these. I certainly hope that I am back, but we will see. But that's all for now. I hope that you are staying happy and healthy, and I'll see you very shortly. Bye for now.